All right, Unit 6. So Unit 6 is all about, we're going to review solution stoichiometry. So hopefully you remember a lot of this from Chem 1. And then later on in the unit in class, we will be talking about solubility equilibrium. Last unit, I introduced to you equilibrium, which is a huge part of AP Chemistry. And there are different parts of equilibrium. So in this unit, we'll talk about solubility equilibrium, which looks at ions and whether or not they dissolve or whether or not they dissociate in water. Next unit, we will talk about acid-base equilibrium, and then eventually we'll talk about thermodynamics and how that relates to equilibrium. So there's a bunch of different subsections of equilibrium, and in this unit, Unit 6, we're going to introduce the first one called solubility equilibrium. But before that, I'm going to review some solution stoichiometry stuff that we reviewed last unit, and also some stuff that should be familiar to you from Chem 1. So we're talking about solutions, so it's really important that you know all about water, and some important facts about water that you need to know is it is a very common solvent. In fact, every single solution, unless you are told otherwise in this class, is going to be some sort of aqueous or aqueous solution, and so water is going to be the solvent. It is the most common solvent. It's called the universal solvent, so it's incredibly important. And two of the reasons, well, actually three, the third one's on the next slide. So some of the reasons why water is so important is because of its structure. And so its structure, and you can look up on the VSEPR chart, but this is one structure that you should know. It is bent. And here's a picture of it over here on the right side, or if you think about it in terms of your Lewis structure, you are going to have water, and then you'll have its two lone pairs here creating this bond angle. Now, if you were to look it up on a chart that we reviewed in Chem 1, and we'll do it later on in the year, we say it's 109.5 degrees. Now, because of the size of the hydrogen molecules in comparison to the oxygen molecule, this bond angle is a little bit smaller. It's actually 105 degrees. Some resources say 104.5. I'm not going to be too picky, nor is the AP exam going to be too picky. If you remember that VSEPR chart, 109.5 is fine. And we'll talk about that more in Unit 11 when we talk about bonding. But just if you look at 109, that's fine. Another really important part of water, and in fact, I would say it's probably the most important aspect of water that allows it to have the characteristics that it does, is the fact it's because of its polarity. Water is very polar, and because the electronegativity of oxygen is greater than the electronegativity of the hydrogen atoms, this creates a dipole moment. And if you remember, a dipole moment just shows the unequal distribution of electrons. And so it shows that the hydrogen is pulling on the electrons a little bit less than the oxygen, or I should say the oxygen is pulling on the electrons a little bit more. If you think about it in a tug of war situation, if we personify the atoms a little bit, we would say that oxygen is stronger than hydrogen and it's pulling on that tug of war a little bit more. And in doing that, it creates this partial negative charge, and hydrogen then in turn has a partial positive charge, and it creates a dipole moment. And so you have your oxygen in the middle and the hydrogen. Now I'm not going to draw the lone pair. Well, I will. The lone pairs are there. Because this has a partial positive and your oxygen has a partial negative, we can draw the dipole moment, which just shows the unequal distribution of electrons, to be in the towards the oxygen. So it kind of goes upwards. Now, you could draw the individual, so I could draw one dipole moment going here and one dipole moment going here if we're talking about each of the individual bonds, but we often just look at the net dipole moment, and so these two dipole moments often are going to be drawn converged together, and one net dipole moment. Now, we will be going into much more detail about dipole moments and why they're important, what they're used for in Unit 11 when we talk about chemical bonding. But for right now, you just need to be aware that the water molecule is very polar. There is a dipole moment, and when the dipole moment is created, your hydrogens are going to have a partial positive charge, while the oxygen will have a partial negative charge. That's going to come into play with the next topic that we're going to review. And that topic is called hydration. Now, we have talked about this in Chem 1. We even mentioned it last unit, but maybe not using this term. And so hydration, the term hydration, means exactly what I was saying. It's so when the positive ends of the water are attracted to the negative anions and the negative ends of the water are connected to or attracted to the positive cations of some other substance. This is exactly how a salt molecule or any ionic compound has the ability to dissociate or to break apart, dissolve, fall apart, break into ions. All those things mean the same. And the process by which this dissociation happens is also called hydration. And so if we look at this green and gray, we'll just say salt crystal here, all the little red and white molecules are the water. And so the water molecule, you have the hydrogen ions are the partial positive. They're going to be attracted to this negative anion here, and they're going to pull it away as it shows up here in this corner. And the negative part, excuse me, the positive part of the water here, the oxygen is going to be attracted to the positive part, the positive ion of the salt, and is going to pull it away like it shows here, which is exactly what dissociation is. It's breaking apart some sort of ionic compound in water, so breaking it apart into its individual ions, and the process by which this happens is called hydration. Now, I've mentioned it a few times, but just remember that this only happens in ionic compounds. And the reason for that is because covalent or molecular compounds don't have ions. So there can't be this positive and negative attraction that happens with hydration. And we talked about this last unit when we talked about solubility, but just as a reminder, if something has the ability to completely dissociate or that hydration process happens, it's going to affect its conductivity and its electrolyte. So if something completely dissociates, as a reminder, that term is called a strong electrolyte. If something only partially dissociates, we would call that a weak electrolyte. Hopefully these terms are familiar to you. And then if you have something that is not an ionic compound at all, so they're not going to have any ions, that would be a non-electrolyte. And the ability for an electrolyte to conduct electricity is directly proportional to these terms that we talked about and how much it dissociates. And so a strong electrolyte, as you can see here, has the brightest light bulb, so it has the highest conductivity, whereas this non-electrolyte, it's not lit up at all. There is no conductivity whatsoever. And then a weak electrolyte, you might get some illumination with that light bulb, but not a whole lot, not enough for any sort of significant value. But just remember these terms that we talked about in Chem 1, strong electrolyte, weak electrolyte, non-electrolyte, and how it compares to some solution's ability to conduct electricity. All right, and I put these here, the solubility rules, just because I know we talked about them in depth last unit, but net ionic equations are still going to be useful in this unit, and so I just wanted to put the solubility rules here for you so you can just reference them in this unit rather than having to go back and find them from your previous notes. And remember, you do not need to memorize these for the AP exam. And as I told you last unit, I would say that these two units, these two bullet points, parts of the solubility rules, the things that will always be soluble, the College Board is going to expect that you know those, but in terms of the other ones, there will be something written in the question that will lead you to these rules that you don't need to memorize them, but you should know the first two, the things that are always soluble. But again, that's just here for your reference so you don't have to keep flipping back and forth to previous units when you're writing your net ionic equations. All right, this is a slide that just has some vocabulary that hopefully none of it is new. We talked about it last unit, and we certainly spent a lot of time on it in Chem 1. And so when you're looking at a solution, or when two things are mixed and we plan to perform calculations about them, it's important to know two things. You need to know the nature of the reaction, so whether you're looking at ions or you're looking at molecular compounds, things like that, solids, liquids, gases, aqueous things, that's what it means by the nature of the reaction. And the second thing you need to know, obviously for mathematical reasons, you need to know the amounts of each. So whether you have grams or moles or molarity, things like that, you need to know the amounts. The second thing under the composition of solutions that you will need to be aware of is molarity. And remember, molarity is another name for concentration. And we use the capital M as the symbol as well as the unit for molarity. The definition of molarity is the moles of solute per volume of solution in liters. And the equation for molarity is going to be that moles of solute divided by liters of solution. But remember that we also took this equation and rearranged it so that the molarity times the volume is equal to moles. And in doing that, you can think about your stoichiometry equivalency thing that we're using for proportions, where if moles is on the top, you put 1 times the coefficient on the bottom. And because these two things are equal, if you have molarity times volume, you're also going to put 1 times the coefficient on the bottom. And that just allows you to do some stoichiometry without having to rearrange this equation. It's kind of done for you. The one thing that we didn't talk about too much in Chem 1 is looking at the molarity of ions. Now, the molarity of the entire solution is not always going to be the same as the molarity of the individual ions. And so it's important to look at that. And really, it just comes down to doing one extra step by looking at the dissociation of the ions and figuring out how many cations you have, how many anions you have, and how that relates to the overall concentration of the solution. And there are some examples that we will talk about to show you how to do that. And we'll do some examples in class. So you'll be able to figure that out. The next thing is standard solution. This is just a vocabulary term. We'll do a lab later on in the semester and the year that has you standardize a solution. And so if we're talking about a standard solution, just a solution whose concentration is accurately known. It's not one that we have estimated, it's one that's accurately known. The next term is a dilution. And so when you dilute something, you are adding water to it, which increases the volume of the overall solution, and in doing that, the molarity of the solution is lowered. And remember that the dilution formula that you will use is M1 times V1 is equal to M2 times V2. And then the one additional step that sometimes questions bring in is ask you to find the amount of water. So it tells you that a solution has been diluted and asks you how much water was added. And just as a reminder, when you are doing those types of questions, you need to take the final volume and subtract the initial volume from that. It's just one extra step that a lot of students forget. So just don't, you're reading those questions carefully. And finally, when we're diluting something, you're going to use a pipette. And there are 2 different types of pipettes. And so it's important that you know the difference and when you would use one versus the other. First of all, there are these things called volumetric pipettes, which I'm not sure if we've used before. I know we used the measuring ones before, but the volumetric ones are a little bit less common. But using a volumetric pipette, they are designed to measure only one volume. So it's kind of like a volumetric flask. You have a 10 milliliter volumetric pipette, it's only going to measure 10 milliliters, nothing more, nothing less, it's going to be exact. Whereas a measuring pipette is graduated, and so it has the ability to measure a variety of measurements. And in the next video, we will go through some examples of molarity and dilution calculations, just as a reminder of how to do them.